Thank you. So I'd like to thank the organizer. So today I want to speak about the big mapping class group, and more precisely about the mapping class group of the plane minus a Cantor set. So first I will define this group and give some motivations. So we need a Cantor set embedded in the plane. So for example here you can take the triadic Cantor set. So you can also represent it this way. So the plane is seen as the sphere minus infinity here, and here you have the Cantor set. And so this is another representation where the Cantor set is here, and here you are infinity. So this is the surface I want to talk about. And so now you can consider the group of homomorphisms of the surface. So preserving orientation. So I will denote it this way. So it's all the homomorphism of the plane, preserving orientation. And preserving the Cantor set. So we don't necessarily fix the Cantor set point-wise. You can exchange some points, but you preserve the whole Cantor set. So now we want to understand the group, so the mapping class group of the plane minus a Cantor set. So it's just this group here, quotienting by isotopy. So two homomorphisms will be isotope if you have a continuous path between them in the group, and you quotient by this equivalence relation. So it's like taking the connected component of your group. So yeah, we want to study that group and its subgroups. So first I will give some motivations which have been given by Gianni Calegari. So coming from dynamics, so if you consider group action and surfaces, so this is an open question. Does there exist any finitely generated and torsion-free group which is not a subgroup of the group of homomorphism of the plane? So we have many examples of group acting on the plane, but it's much more harder to find a group which is not acting on the plane. So yeah, so there is the Zimmer program dealing with this kind of questions, and usually you need to add some rigidity to give some answers, like for example diffeomorphism preserving area or diffeomorphism. But it's hard to tell something if you just ask for homomorphisms. So yeah, so in this setting, you can see the mapping class group of the plane minus a Cantor set arriving this way. So you assume that you have a group G acting on the plane, so a subgroup of the group of homomorphism of the plane with a bounded orbit. So then there will be a natural morphism from this group to the mapping class group of the plane minus K, where K is either finite or a Cantor set. So I will explain you how to get that morphism. So here I have a group G, and this is the orbit of G, so it's bounded in the plane. Now I can consider the closure of the orbit of P here. So G is preserving the orbits, and it's still preserving the closure of the orbits. So G will also preserve the bounded component of the complement of this closure. So here maybe these two components will be exchanged, but they will be preserved. So G is still acting on this, and now we can collapse all components. So you just quotient by the relation being in the same connected component, and you get a totally, discontinuous set here, here. G is still preserving that set, and so now you can consider a minimal orbit for this action, and you will get a minimal set here, which is in red. And so this minimal subset will be either finite or a Cantor set. So if K is finite, you get more or less a braid group. And if K is not finite, well, you have here the Cantor set. So this morphism, if you have like restriction, and if you understand well the subgroup here, you can hope to get restriction on action of G on the plane with bounded orbits. So that's the general idea. So yeah, that's the first motivation. So second motivation is about the Artinization of subgroup of the group of homomorphism of the Cantor set itself. So if you take a subgroup of the Cantor set here, so for example, Thomson group of a group of automorphism of the shifts, you want to understand that group. The idea is to consider a subgroup of the mapping class group which surjects on your group. So you have this diagram. So here, G tilde will be a subgroup of the mapping class group which surjects on your group G. And so if you understand well the subgroup of the mapping class group, you can hope to tell something about your group G with this action. Okay, so here will be the general idea of the talk. So to study a group G, well, it's useful to have a delta hyperbolic metric space X on which your group acts by isometries. So I just recall quickly the definition of delta hyperbolic. So space is said to be delta hyperbolic if you have a delta such that each triangle is delta sim, like here. But yeah, like the Euclidean plane is not delta hyperbolic. So if you have an action of a group G on a delta hyperbolic space X, then you can classify the element of G. So they will be either elliptic, parabolic, or loxodromic. And so, well, usually if you have loxodromic elements, you will be able to say, you will be able to try to say interesting thing about your group. So for example, if you have two independent loxodromic elements, you will construct a subgroup, a free subgroup of your group G. So in the setting of the group action on the plane, for example, if you know that your group has no free subgroup, then if you understand well the loxodromic elements of the mapping class group, you will be able to say that your group is not acting with two independent loxodromic elements. And you can also construct subgroup invariants like quasimorphism and bounded cohomology, etc. So today, yeah, so we will be looking for hyperbolic space for the mapping class group of the plane minus the Cantor set. So first I will speak about mapping class group of finite type surfaces, so which are like surface with finite genus and possibly with finitely many punctures. So they act on the curve graph. So I will recall some definition here. And then I will speak about the mapping class group of the plane minus the Cantor set. So I will define the ray graph. So describe a geodesic on the graph and give an example of a loxodromic element. So the ray graph will be a hyperbolic space for this group here. And then I will give a description of the boundary of this ray graph. So this is a joint work with Alden Walker. Okay, so first, well, mapping class groups are finite type surfaces. So for this type of mapping class groups, there is a curve graph which has been defined by Harvey. So the vertices are isotopy classes of essential simple closed curve. So simple closed curve on the surface is said to be essential if it's not isotropic to a point. Okay, like these two here are not essential. Okay, you can just move it to a point here. So you take all the isotopy class of simple closed curve. So here I give an example of 3 of them. And then So you put an edge between two vertices if the curves are homotopically disjoint. So here, for example, we get an edge between the blue curve and the red curve, and an edge between the green curve and the red curve. So you get a graph this way. Okay, you have vertices and edges, and then you put a metric on your graph saying that each edge has length 1. So here, for example, the red curve and the green curve and the blue curve will be at distance 2 in the graph. So the mapping class group of the surface acts on this graph because if you take a curve, the action is just taking the image of the curve by the homomorphism, and you take everything up to isotopy. And so it acts by isometries because if you take two different curves, they will be sent to two different curves by any homomorphism. And so Mazur and Minsky proved that the curve graphs are delta hyperbolic. Yeah. So this gives, well, and the action is interesting. Like there are many loxonomic elements and gives a lot of information for studies the mapping gas group of finite type surfaces. Do you have any questions? Yeah.
Why are the blue and the green homotopically?
Because you cannot, well, there is no homotopy between the blue and the green. No, they're not different.
Sorry.
No, here, okay.
Yeah, right.
Okay, so yeah, then you can classify homomorphism of the surface. Just you look at the class in the mapping cat group, and you look at the action on the graph, and you can say if it's parabolic, loxonomic, or elliptic, and classify the homomorphism this way. Okay, so now back to the plane minus a counter set. You can also define the curve graph in the same way. So you take all the curves, and well, what you can see here is that this graph has diameter 2. So it won't be interesting. Yeah, so I didn't say it, but a loxonomic element is an element which acts by translation on a quasi-ax. So you need infinite diameter if you want to tell something about your group. So here, this graph has diameter 2 because if you take any two curves, even if they are really complicated, now if you look at the complement of these two curves, you take a point of the counter sets, and because the counter set, each point is an accumulation point, you will be able to draw here a curve which is non-essential and which is different from both. So for any two curve, you can find a curve which is different from both. So that's proof that the graph has diameter 2. So we can't use the curve graph for to study like big mapping class groups. So Danny Caligari defined another graph specific to the plane minus a counter set. So this is the plane minus a counter set. Infinity is here. So now I will draw it this way. So this is infinity. This is the counter set, and you have to think about it as a sphere. Like we can go back. So first, we want to define vertices. So a vertex here will be an isotopy class of simple arc between infinity and the point of the counter set, like this. So this is a vertex, and of course, you have many of them. So this gives you like a bunch of vertices, and now the same idea then for the curve complex, for the curve graph, sorry. You put an edge between two vertices if and only if the rays, the arcs are different up to isotopy fixing the counter set. So here we get an edge between the green and the red, an edge between the blue and the green, but no edge between the red and the blue arcs. So we have well, we have a graph. So note that this graph is big in the sense that, well, here, for example, you have uncountably many different arcs different rays, like this. Well, you take all the rays going from infinity to the counter set. So each vertex will be actually part of an uncoutable clique. So meaning that the graph is not proper, and it's far from being proper, actually. So the mapping class group of the plane minus the counter set acts on this graph by isometry, for the same reason that the mapping class group of any surface acts on the curve graph by isometry. Okay, if you take two different rays, you act on it by homeomorphism, you get, again, two different rays. So this preserves the edges. So we get an action by isometry on a graph. So it will be nice if this graph could be hyperbolic. So yeah, the mapping class group acts by isometry on the graph, and the graph is connected. So we have this following theorem. So this ray graph has infinite diameter and is delta hyperbolic. So once we have this, we can start to play and act and classify the element of the mapping class group, etc. Do you have any questions? Okay. Yeah. So this is an analogous of the curve graph for this surface. So now I will give you a description of an infinite geodesic of this graph. So this will in particular prove that the graph has infinite diameter. Okay, so I will give you a sequence of ray alpha k such that the distance between alpha 0 and alpha k is equal to k for all k. Okay, so this will give, well, an infinite, actually it's an infinite geodesic. Okay, so first we start with two rays at distance 2. So here beta and alpha 0. So it's easy to draw rays at distance 2. Basically, you take any two rays that you can think about at first, and they will be at distance 2. Because if you want to be at distance 3, well, wait. Okay, so there are distance 2, yeah. If you want to be at distance 3 in the graph, so if I have alpha and beta at distance 3, that means that any ray which is different from alpha has to intersect beta. So if you want to draw two rays, alpha and beta, at distance 3, you have to be sure that any ray which is different from alpha intersects beta. So you have to have, you need a control on all the rays different from alpha. So the idea here is to do the following. So you start with alpha 0. And so I want to draw alpha 1, which is at distance 3 from beta. So I just follow alpha 0 this way. Then I turn around a chunk of counter set, and I go back to infinity. I turn around infinity, and I follow alpha 0 one more time. So I get alpha 1 this way, and I claim that the distance between beta and alpha 1 is equal to 3. So we need to check that any ray different from alpha 1 intersects beta. So beta is this curve here. And so actually, if you take a ray which is different from alpha 1, so here you need to draw an arc which starts at infinity and goes to the counter set. So you have two possibilities. Either you go this way, and once you find the counter set, you can attach to it or turn around or do whatever you want, or you go in the other component and you do this. So in both cases, you have to do like to follow one of the two green lines, and so you have to intersect beta. Okay, maybe, yeah, beta is like that. So this means that, well, if you, in the graph, if you take the sphere of radius 1 around alpha 0, around alpha 1, they will all begin like alpha 0, and they will all intersect beta. So alpha 1 will be at distance 3 from beta. So yeah. So now we want to draw alpha 2 at distance 4 from beta. So we can use the same idea. So you just follow alpha 1 this way. Up. So once we arrive at the Cantor set, we just turn around it and go back to infinity. Like, we just want to draw a tube around alpha 1. Up. And once we arrive at infinity, we go back to the Cantor set. So we follow alpha 1 last time. So we get alpha 2. And so now I'm claiming that any ray at distance 1 from alpha 2 begins like alpha 1, so it will be at distance 2 from from beta. So yeah, if you want to be different from alpha 2, you have to begin either like this or like this, meaning that you begin like alpha 1. And so any ray at distance 2 from alpha 2 begins like alpha 0 and intersects beta. So yeah, so the whole, this is alpha 2. If you take a disk, like a sphere around alpha 2, it will begin like the red one. If you take a sphere of radius 2 around alpha 2, it will begin like the green ray alpha 0 here. So it will intersect beta. So this gives you distance 4 in the graph. So now if you want to draw a ray at distance 5, you just do the same thing. So I won't draw it, but you get something like this here. So this is alpha 3. You just draw a tube around alpha 2. And for any k, by induction, you can draw alpha k such that the distance between beta and alpha k is equal to k plus 2. So you get alpha 4, alpha 5, and then, well, they all look similar. So, yeah, so we have this way we get, maybe I should draw here. We get, well, actually it's a geodesic, so you get alpha 1, alpha 2, etc. So this proves that the graph has infinite diameter. So then there exists elements of the mapping class group with a loxonomic action on the ray graph. So loxonomic action means that you act by translation. So here, if you take this braid, so this is a Cantor set with infinity, and you just move the chunk of Cantor set this way around infinity, and then you translate everyone here. These elements will act by translation on the geodesic here, because yeah, you can prove that, well, if this is age, then age of alpha k is equal to alpha k plus 1. So this gives you an element like this. So this will be loxodromic. So yeah. Okay, so now I'd like to speak about the boundary of this graph. So whenever you have delta hyperbolic space, there is a definition of Gromov boundary. So it's a set of equivalence classes of half quasi-geodesic, where two quasi-geodesic are equivalent if they stay at bounded distance. So for example, if you take the hyperbolic plane here, well, the boundary will be the circle. And so, well, there is like a definition, an abstract definition like this. And so we wanted to understand, well, we wanted to get a representation of this abstract definition in terms of rays on the surface. So for finite type surfaces, there is a nice characterization of this boundary. So for finite type surfaces, we have seen that we have a curve graph, and the boundary can be described in terms of minimal filling geodesic laminations. So here, for the plane minus a Cantor set, now we have the ray graph, and so we wanted to give a description of the boundary. So yeah, so for example, well, if you think about this geodesic here, because it's a geodesic, it should correspond to a point, well, x in the boundary of the graph. And so we have, well, here alpha 0, alpha 1, etc. So you can define by induction some alpha infinite. And so you can say, okay, I want this alpha infinite to be the boundary point for this geodesic. But then you need to check that any geodesic which is close to this one will go to the same boundary point. And also you need to check that you can describe it in the same way for any half geodesic or half quasi-geodesic in the graph. Okay. So yeah, to do that, so I will first describe some tools that we will use later. So yeah, we need some compacity. So we will on the graph. So we will get compacity as a conical cover. We will define a natural injection from the ray graph to a circle, and from this circle we will get compacity. Yeah, because the set of lamination on this surface is not compact, so we can't really use laminations. So then we will define a bigger graph, the completed ray graph. So we will add some rays in the ray graph that we already have, and so we will get a description of this bigger graph and a notification between some of its components and the Gromov boundary of the usual ray graph, and a natural topology on this boundary. Okay. So yeah, so I start with the conical cover. So we want to find an injection from the ray graph, well, from the vertices of the ray graph to the circle. So yeah, I want to use the universal cover of the plane minus a Cantor set, but because it's easier to think about, it's easier to think about the sphere minus 4 points than to think about the sphere minus infinity and a Cantor set. And the idea is exactly the same, so I will first explain it on the sphere minus 4 points. So we have a sphere with 4 punctures here. So this is the universal cover. So this is a fundamental domain. Okay, I can lift the north hemisphere here and the south hemisphere here. And so this domain tessellates the whole plane this way. So now, well, if I want to lift, for example, this loop here, if I choose a lift of this point here in this domain, then there is a unique way to lift this loop. Okay, I need to go through the equator segment, which is between the red and the grid points here, and then I need to go there. So yeah, from this lift, if I choose a lift of the origin, then there is a unique way to lift my loop. But if I want to lift now a ray, like an arc between, for example, these 2 points, I can choose a lift. So I choose this lift, and now I have infinitely many choices. Okay, if I want to lift that purple ray from this point, I can start in any fundamental domain which is here, so I have infinitely many choices to lift this arc. So what we can do, because we want only one choice, so what you can do is you quotient this picture by the parabolic elements here. So here I want to say, okay, I just keep this part of the universal cover. So now if I do that, I have only one choice. I have to go there. So to force all my lifts to go there, I just need to quotient by the parabolic elements here in the function group, which send this ray to this one. So I get a conical cover here. And so, well, this is the same cover but seen from the top. And here now, if I want to lift this arc, I have only, if I choose this lift, I have only one possibility to lift my arc. So, yeah, so we can do the same thing for the plane minus a Cantor set here. So this is a fundamental domain for this surface. This is like the whole tessellation. And now I want to quotient this picture by the parabolic element here. So I get this, which can be seen as this here. And now for any ray, I have a unique lift in this picture, which starts at this point. And so if I choose any ray here, I will get a unique point on the boundary of this cover, meaning that I will get an injection from the ray graph to the boundary of this conical cover, like this. Okay, so now, yeah, for each ray, I have a unique point of the boundary. So now you can ask, okay, what are the other points of the boundary? What do I get if I choose any point on the boundary and I draw the geodesic on the surface? So you can get, well, short rays, so the rays from infinity and which stop at the Cantor set. You can get geodesic with self-intersections. So we won't be interested in this kind of geodesic. So you forget about all the points which correspond to geodesic with self-intersection. And so what else do we get? We get loops. So if you take a ray which goes to on the boundary to a lift of infinity, you will get a loop. Okay, you will go back to infinity. And so you will also get what we call long rays. So these are rays which never stop on the surface. So they don't go to the Cantor sets. Oops. Yeah, they never go back to the Cantor set or to infinity. They just intersect infinitely many equator segments. So we have three kind of different rays. So yeah, so we were interested in the short rays here, but now we have two other kind of rays. So we will just put all of them in the same graph. So we get a huge graph, so that we call the completed ray graph. So in that graph, you have the vertices will be isotopy class of short rays, loops, or long rays. So short rays, loops, and long rays. So in particular, this graph contains the short ray graph that we were interested about. So now, well, like usual, you put an edge between two vertices if and only if they have different representative. So here we have an edge between the green and the blue one. So first remark, this graph is not connected. So why is it not connected? Because this ray, there is no rays different from this one. So this ray is just like alpha infinite. So the ray here that we get by induction doing alpha k, here we can define some ray alpha infinite. And so by construction, we say that any ray different from alpha k has to begin like alpha k minus 1. So any ray different from alpha infinite has to begin like alpha infinite. So there is no ray different from alpha infinite. So this ray, well, it's a connected component of the completed ray graph. So what else can we say about this graph? So we can describe all the connected components of the graph. So first, there is a huge connected component that we call the main component. So it's quasi-isometric to the usual ray graph. So it's the component who contains the usual ray graph, so all the short rays, and which also contains the loops and some long rays. So this graph actually has infinite diameter and is quasi-isometric to the usual ray graph. And all the other components are cliques, so like completed graph. So graph of diameter 0 or 1. So the picture is like that. So this is like quasi-isometric to the ray graph that we wanted to understand, and around it we have infinitely many cliques. So like alpha infinite is one of them, and you have also cliques of diameter 1. So this is an example of clique. This is alpha infinite here. This is another example of a clique with 3 elements in it. So these are like 3 long rays, a green, blue, and red, and they all intersect all the short rays. They all intersect all the loops, and more than intersecting them, they are at infinite distance from them in the graph. So yeah, so we have many examples of cliques like this. And so actually what we will prove is that each point of the boundary of the usual ray graph will be, we will get a bijection between the point of the boundary and these cliques. So each point of the boundary will be a clique like this. Like this will be the point of the boundary for this geodesic as we wanted, for example. So yeah, so there exists a natural bijection between the Gromov boundary of the ray graph, so which is here, and the set of cliques of the completed ray graph. So yeah, to understand how this bijection works, so if I take a quasi-geodesic of the ray graph here, which goes to infinity, so I have a sequence of rays, and I can see it on the boundary of the conical cover. Okay, because there is an injection from the rays to the boundary here. So now I have a subset of the circle, and because the circle is compact, I have a limit set which is non-empty. And so this limit set, actually, we can prove that this limit set is included in the same clique. So all the elements that you get in the limit sets, they're all long rays, they're all like infinitely far from any loop, for example, and they all disjoint. And so if you take another quasi-geodesic which corresponds to the same point at infinity, so which stay close from the first one, then the two limit sets will be included in the same clique. So because of this, you can define a map which sends every point of the Gromov boundary to the clique which contains the limit set of any representative quasi-geodesic. And so we prove that this map is a bijection. Okay, so now we have three versions of the same point of the Gromov boundary. So we have the version, well, here as a connected component of the completed graph. We have here, well, the graph, the three rays, well, the rays on the surface, and we have the subsets of the boundary of the conical cover. So yeah, so now there is a natural topology on the Gromov boundary of the ray graph, which is just given by the abstract definition. So it's a Gromov topology. And there is also a natural topology on the set of cliques. Okay, because we have a topology on the circle, which is the usual topology. And because if you take all the rays which are on the cliques, you get a subset of the circle, and then you quotient that set by the equivalence relation being in the same clique. So you will get a quotient topology on this set. And so the theorem is that the bijection that we define is actually a homomorphism. So like the characterization is natural in this sense. Okay. So now, so Alden Walker, my collaborator, he did a great program to draw pictures, so I wanted to show you some of them. So yeah, we'll give you examples of loxonomic actions. So as I said, loxonomic elements is acting by translation on some quasi-axis. So in the graph here, we have an action. If I take a loxonomic element, I have an action here, and it fixes two boundary points. So we have two cliques which are fixed by the loxonomic element. So yeah, there are two fixed points, one attracting and one repelling here, and they correspond to two cliques of rays on the boundary here. So I want to, for every ray, then you can look at the orbit of your ray when you apply H, and well, by the construction, we're supposed to see these orbits which accumulates to C plus or to C minus, to the two cliques. We're supposed to be able to see the cliques when you apply H. So yeah, so for example here. So I take H, the element which acts by translation here, on alpha 0, alpha 1, alpha 2. So we know what is the action on alpha 0, because we know it's going this way. But now if I take any ray, what will be the action? So actually they begin more and more like the long ray alpha infinite. So here I apply the element H on these 3 rays. So if I apply it once, twice, so you can see that, well, the ray, they begins more and more like infinite. And this is because on the boundary of the conical cover, they accumulate to alpha infinite. Oops. So this is a second example. So this is an example with an element H, which are more than 1 ray in the clique. Okay, so I start with 2 rays, and I apply H. So once, twice. And so here you can see, well, it looks like the pattern is the same on both pictures, but you can see that the 2 rays don't start in the same way. Like one will go there, and the other one we don't really know. But actually, if you zoom here, you can see that the 2 rays are not the same. Like there are one start here and the other one start here. So their endpoints in the boundary of the conical cover will be really far away, but still they will be in the same clique because they are disjoint. If you look at the clique. So third example, so H is these elements again, which act by translation on alpha k, and I want to see what is C minus. Like we know that C plus looks like alpha infinite. So what does C minus look like? So here we apply H squared to the red one and H inverse to the blue one. And so here you can see that, well, C plus will be the red one and C minus will look like the blue one. So you can see both cliques on the same picture this way. And so last example, well, for the other loxonomic elements, again, I apply H and H inverse on 2 rays. And here, well, we get 2 really different cliques, okay? So like this picture is really symmetric, but it really comes from the symmetry of the braid that we apply. So if you apply any loxonomic braid, there is no reason why you will get something symmetric. Okay, I will stop there.
You threw away some of the circle, right? Because you threw away the rays that corresponded to self-intersecting.
I can't hear you.
Sorry, you threw away some of the circle, right? Because you threw away the
the one with auto intersection?
Yeah. So
yeah.
I would imagine that's quite a lot of the circle. Is that right?
Yeah.
Can you sort of tell can you characterize how much of the circle, which subset of the circle you're looking at?
It's an open set.
An open. Is it a dense?
It's an open subset of the circle. So what you get is a closed subset of the circle. So you still have compacity.
I see. So you threw away an open subset. I see.
Yeah. That's why we still have compacity. Yeah.
Right.
Yes.
So you studied the situation in dimension 2, but what is the answer in dimension 1?
Sorry, I can't.
What is the answer in dimension 1?
For
all these questions you studied.
Here, so in dimension 1, there are examples of groups which doesn't act like faithfully on the circle by homomorphism. So for example, height rank lattices, they will have a finite image on the group of homomorphisms.
Is there some characterization? Or
what do you mean by characterization?
groups which don't act? Yes? Not
I
examples.
Yes, okay, yeah. Yeah, but that's just the definition, right? Yeah. Like this one actually, the mapping group of the plane minus the Cantor sets acts on a circle by homomorphism. Like there is it's a subgroup of the group of homomorphism of the circle. But, yeah.
Question?